Welcome to the final lecture on support vector machines. What we did previously was to, coming back to the same figure, we found a maximum merging separating hyperplane, and what we did was, correct this. What we did was to found out a line and which has the highest margin of separation with the closest point from both classes. And this boundary we called as a maximum margin hyperplane or a support vector machine. And the way we started was, we initially sort of put the constant that for given w x plus b equals to 0, where w is a vector and x is this x2 vector, we started was that for x I should have into y I to be greater than equal to 0. Okay. So, the plus points are in plus side, minus points are in minus side. In fact, we sort of said that this is equivalent to scaling w and b, so that we have the minimum value to be not just 0, but also 1. Okay. So, this was our constant. Okay. And then we maximize the margin given satisfying that constant. So, we actually observe that there will be, if we have classes like this, there will be infinite lines, we pick up the one with the highest margin. But suppose the case is like this instead. There is overlap and we cannot find any line which will satisfy for overlapping classes. So, you have like this. cannot draw a line. Okay. So, what to do? So, what I do is introduce some slack variable and relax the constants. Replace them by some slack xi. Okay, some relaxation. So, what is the meaning of this? This was the margin, and the closest point was at a distance of 1, not distance, and a value of 1. Okay. Now, inside the margin we can have points. This, if I draw clearly, this was the hard margin. Closest point is at 1. Now, we have 1 minus xi I. So, there is a point inside also. Some points can be inside the margin. It is no longer a no man's land. Okay. So, this is called a soft margin. Slack by some xi I. Let me properly write it. Xi I, allow slack. Okay. So, if I rewrite my optimization problem, it becomes sorry. Such that not 1, but 1 minus xi I. Okay. So, slack. But we don't want to have too much psi I. So, add it as a note that every point x I will have a slack xi I. Minimize this and multiply these two factor by a constant c. Okay. So, see this c I called constant. It controls. So, this is clear. This is my new optimization problem, new constant, new objective function. Constant I add slack, objective function I penalize slack. Okay. So, if I look, if I write again, this is the margin 1 by this error. So, it controls generalization error and this is the training set error. This is the error. Controls error. Okay. It does that. All right. So, let us try to solve this. The dual problem looks like this. If we transform, we will see with all the operation that we do earlier, same form, alpha I are the Lagrange multipliers, Okay. Same, only constant changes. Earlier we had the constant alpha I greater than equal to 0 for all I. Now we have the constant alpha I greater than equal to 0 and less than the generalization constant. Okay. So, you solve it in the for all I. Okay. Solve it in the same way as earlier quadratic programming. You get your support vectors, you still get xi. Okay, you still get that. Okay. So, in practice we use the soft margin hyperplane. Same process. See, everything remains the same except for the constant of the QP changes. One upper bound on alpha is at there. Okay, that is the only difference. So, exactly same way, right. So, all the softwares you use for SVM will have this soft margin actually, not the hard margin. So, you have to choose a value of C, right. Now, let us come to another case. Now, let us come, suppose okay. So, you cannot draw a line, but you can draw a nonlinear surface. To separate them. So, how to solve this problem? The problem is solved by something known as a kernel trick. So, what is the trick? So, phi transform Z such that the classes are separable in the Z space. Okay. So, you map it to high dimension and then draw a line as it is, but not on x, but on z. Done using a kernel function. What the kernel function does is that it takes two vector x 1 and x 2 and returns a similarity score between them. So, the dot product it takes two is an example, takes two vector, returns the cosine of the angle between them. Okay. That is called the linear kernel. Okay. That is called the linear kernel. So, what happens is that, let me add this. Kernel. I am actually not going into the theory, there is a nice mathematical theory. Maybe if you ask question in the forum, I will give you the details, because this is I am just giving the overview. So, if you remember what we did, our minimize the dual form was, if you remember again, minimize, we took a vector of alphas minus, if you remember, we used a Hessian matrix H and C. So, what was the Hessian matrix? H I j was y I y j times x I dot x j, dot product, linear kernel. We just generalize this, instead of x I dot x j, we write y I y j k of x I x j. Okay. Kernel of x I x j, it takes two vector, returns a scalar, positive definite, it should always be positive definite. Okay. So, one property is that this Hessian matrix would always be something called a positive definite matrix. Matrix is always positive definite. Okay. So, you just form this Hessian and just plug in that value of Hessian here, and rest is as it is, same W equal to summation alpha I x I for the support vector, same thing, it does everything. And you have several examples of kernel function. Linear kernel. So, two property a kernel function should have. It should return a scalar, okay, and it return some value, positive value. x1, x2 are two vectors, x1 it is x1 dot xj. Okay. Polynomial kernel, x1, x2 x1 dot d, dth order, Gaussian kernel or sometimes known as the RBF kernel, radial basis function kernel, is sigma. Okay. Many other kernel, even for discrete other cases are proposed. Okay. So, you can choose your kernel accordingly and just use the same support. So, when you use a support vector machine software, you have to specify the value of generalization constant C and what type of kernel you want to use, that is all. It will just plug in, solve QP, everything, give you the support vectors, give you W, everything. That is your point. Just one more point, I discussed everything for 2 class, what to do for multi class. Suppose there are more classes. What to do? What you do, split a k class problem into many 2 class problem. How? To approach one against all. So, this against rest one thing, this against rest one, this against rest 3 hyperplane unit. Okay, which is like this. First between these two, then between these two, then between these two. Okay. Both cases you need 3 hyperplanes actually. There are other approach, there is one more approach called a directed acyclic graph, which does a hierarchical tree like splitting, which I am not describing, you can see it. There is optimization problem to solve. Okay. So, this is how these also if you specify in your software how to do, it will do it. Alright. So, this concludes my talk on SVM. You can look up the lecture notes, more details are there. I did not go into some of the mathematics. You can look up and you can try any of the software on some sample problems, which I will give in the exercise. Thank you.